Until about 200 years ago, we humans largely depended for our energy needs on our own muscles, on animals, and on burning wood. When we ran short of wood, we discovered a marvelous source of energy stored in fossil fuels: coal, gas, and oil. Fossil fuels are nothing more than the transformed remains of plants and animals that died millions of years ago. When we burn them, we release the energy of the ancient sunlight that helped create them in the first place. But we have come to be dangerously dependent on fossil fuels, even addicted to them. Not only does that accelerate global warming, we're likely to run out of cheap oil and gas by mid-century. Coal, though much more abundant, is highly toxic. So we must do something urgently. In the developed world, we must learn to use less energy. A 50% reduction may be necessary. And we must turn increasingly to renewable energy sources. One of our most promising solutions may be to turn back to our old friend, the sun. Do you know that the solar energy that strikes the Earth's surface for 1 hour is enough to feed the world's current electricity needs for 1 year? So why haven't we gone solar already? I mean, it's pollution-free, there's no global warming, there's no dependence on foreign oil powers, it's decentralized, so it's virtually terrorist-proof, and effectively, there's an infinite supply. I mean, it sounds like the dream solution, doesn't it? But will it work? This film's all about sunlight, what it is, how we are learning to use it, and what the future may hold. Our story starts, however, long ago and far away. Many ancient peoples worshipped the sun. The Egyptian pharaoh Akhenaten founded the first religion in history to have a single god, and that god was the sun. The writers of the Bible acknowledged its primacy by having God's first instruction be, "Let there be light." But what exactly was this stuff, light? No one had any clear idea until the eminent English scientist Isaac Newton took an educated guess about 300 years ago and wrote, "Are not the rays of light very small bodies emitted from shining substances?"
Well, Newton's idea of light was really quite a simple one. He thought that light consisted of a stream of particles that, as he knew, traveled in straight lines.
Newton's guess was a good one, as Einstein would later show. But a very different guess was made by a Dutchman, Christian Huygens. Huygens observed the waves made by a stone dropped in water. He had a brilliant insight, suggesting that light, as he said, spreads by spherical surfaces and waves. Here's a drawing that Huygens made to illustrate waves of light flowing from a candle. Huygens had created the wave theory of light, but like Newton, he couldn't back up his theory with experimental results. And so things stood until 1803, when a Londoner called Thomas Young was invited to make a presentation on light in the famous lecture theatre at the Royal Institution.
The Royal Institution was founded in 1799, immediately a big hit. People came to be educated, to see, to learn about science. It was almost evidently like a magic show.
These physics students at Stanford University are replicating one of Thomas Young's experiments.
This ring stand for the laser.
Light from a single source must enter two narrow slits and eventually hit a screen some distance away. The reason that Young did this experiment was to try to see if light was a wave or a particle. Was Newton right or Huygens? The light from each slit spreads out like waves of water. Each wave interferes with the others, creating a pattern of light and dark patches.
All across that second screen, its intensity varied across the screen in a very regular way. And that could be perfectly naturally explained by the wave theory and couldn't be explained at all by Newton's theory.
So Christian Huygens' theory was right. Light is a wave. But that's not the end of the story. In the early 19th century, no one thought there was much connection between light, electricity, and magnetism. They seemed like three very different phenomena. Then, here at the Royal Institution, a young scientist called Michael Faraday started doing experiments with an electromagnet, and he discovered that electricity and magnetism were two sides of the same coin. Another British scientist, James Clerk Maxwell, then set out to formulate Faraday's findings mathematically, and his equations predicted the existence of electromagnetic waves.
So Maxwell discovered electromagnetic waves mathematically. He calculated the speed of these waves, and he noticed that it was exactly the same as the speed of light that had previously been measured. So suddenly, he finds himself confronted with this fact that light is a wave phenomenon, and it is an electromagnetic wave phenomenon. One of the great insights of natural science.
German scientist Heinrich Hertz experimented by shining lights on electrical circuits, and results seemed to confirm Maxwell's theory. Our knowledge is complete, said Hertz. A refutation of these views is unthinkable. The wave theory of light is a certainty. However, Hertz's assistant, Philip Lenart, decided to look more closely at one of the experiments where there was a gap in the electrical circuit.
Different colors across the gap. Right now there's no high voltage, so you don't see anything happening.